Hello everyone, welcome to APNIC eLearning. Uh, Today is 19th April 2017, 3 p.m. Uh, Brisbane time from the place we're doing this e-learning today. So today I'll talk about the topics we are going to have is Introduction to SDN. So I'll provide a high-level overview of SDN or software-defined networks and the impact of technology shift on the market and how the way we are doing the way we are building our data networks, right? So it's going to be a roughly 1 hour session. We'll have a session for you to ask me some questions. But if you have any query at any time, feel free to let me know. I'll try to clarify all those issues as we go through, right? Moving forward, a little bit of introduction about myself. My name is Fakrul. I'm the Senior Training Officer in APNIC. So we do provide face-to-face training, remote training, the what we are doing right now. We recently launched our APNIC Academy. So if you're interested, you can visit apnic.academy, or for more details, you can log into training.apnic.net. Right. So the agenda we're going to have for today is we'll start with a look at how routers are evolved and the condition that results in the emergence of SDN. We'll touch on the Stanford Clean Slate project, in particular the development of OpenFlow, and we'll look at the different SDN architectures that are being adopted now together with the key use cases. We'll also touch on the SDO, also known as Standards Development Organizations, that are involved in SDN standardizations effort and two key open source SDN project. And finally, we'll briefly discuss uh, how SDN differs from NAV, because some people might have a confusion about NAV and SDN. They thought it's the same thing, but we'll try to clarify how SDN differs from NAV, network function virtualization. So if you see the routers we have, and if you look at the routers today, we can still say that the fundamental role of routers has not changed since the IMP, also known as Interface Message Processor of the ARPANET project. So they have two key responsibilities. The number one is to determine network paths or the routes. A number of routing protocol, both internal and external, are available today to perform this exam function. So we have a WSPF, ISIS, and IGP. We also have a BGP as a exterior routing protocol. And the next function is to forward packet along the path they have determined. So it's basically these two functions done by the routers. And in summary, we could say that the basic elementary function of a router, or you could say a switch, has not changed much since the inception of data networking. So if you look at this diagram, the way we see our today's routers. So although the fundamental role of the routers has not changed, the capability of the routers have greatly evolved over time. So this evolution has primarily been driven by the variety of applications being carried out over data networks, from email, FTP, telnet, in the early days to the www or World Wide Web, to voice, video, or triple play or multiplay applications, and to an environment where the bulk of the communication is being conducted over an IP network, right? To facilitate these many changes, or these to adopt these capabilities, has been adopted to the routers over time and derived from off management high availability features, multiple service layers, elaborate and complex QoS quality of service mechanism, specialized hardware for specific network function and etc. So there is a multitude of router manufacturer who basically uh, provide all those high capability uh, mechanism to manage all those routers we have today. So the end result is the today's routers is an extremely complex and a costly device. So if you see, there are a lot of small components which does a lot of things, and it creates a lot of complexity the way routers works today. So moving forward, so how we get, or how did we get here, right? So there are a couple of 4 or 5 things that basically motivate or influence us to have these complex components in our routers. So we agree that it's a complex device, and we did it for our to build a complex network, right? So at this point, it is very important to ask ourselves a few questions and see why these current routers design the way it is right now, and how we architect our network and why we need all those components. So the first one is basically distribution of complexity, right? So it's basically a well-known and understood technique in the engineering hierarchy. So we solve complex problem by splitting them into a smaller one or simpler one. So we also know, or sometimes is mentioned as a divide and conquer. So the end-to-end principle takes it to an ultimate level, or relatively dumb connectionless packet forwarding, packet switch infrastructure with a high functionality at the edge. So we scale our networks via the same mechanism. These also provides for better survivability. If one part of the network fails, it will not impact the whole infrastructure. So the impact will be limited or within that scope. And there is no central intelligence whose failure could bring the network to its knees. So we don't, for nowadays, before SDN, we don't have anything which work as a centralized management, which cause severe downtime or complexity within the core network. So the concept is known as inter-domain versus intra-domain routing in the internet, and is a great example of success of an approach. So if you see the way we architect our infrastructure, we use WSPF and ISIS as inter-domain routing protocol, and we have to speak with other external entity. We use BGP as an exterior gateway protocol, or inter-domain routing protocol, and we use ASN to do BGP with this entity. So if you see if there's any complexity of any issues or routing loop or any downtime within our IGP domain, it basically doesn't impact the whole internet as a whole, right? So as data networking is becoming more and more complex and advanced, we have pushed out more complexity to the edge. This is one of the reasons the routers are very complex nowadays. Number two is backward compatibility. So, if you see the history of internet, the last and the most historical flag day in the history of the networking was January 1st, 1983, when the ARPANET changed from NCP or Network Control Program to TCP/IP protocol suite. So they basically switch off NCP and switch on TCP. And that's the major change. After 1983, January 1st, we don't see any major or a flag day where we could say that we shut down the whole internet, we do some maintenance and fine tune and turn on the internet again. So we don't have such days, right? So so what we have ended up with this requirement of for backward compatibility that has constrained protocol development, and prevented any radical new ideas from being adopted. In addition, the industry has been effective at finding non-ideal but practical solutions when faced with challenges. For example, we use CIDR. When we have issue with IPv4 exertion, we start doing NAT. We also have congestion control and so on and so on. So there's so many examples where we make sure that it is backward compatible. Such mechanisms have provided technical solution that didn't question the foundation of underlying networks. Number three is the unanticipated application. So we often say that the field of networking is a victim of its own success. So the IP network is so successful that we start putting everything on IP networks. We start with data, but if you see voice, video, everything is over IP network. So various types of communication have moved to IP infrastructure. It creates a lot of complexity in networking platform as it grows to accommodate all those issues. And we have continued to implement new technologies and solutions on top of our existing one. Uh, Number four is need for higher performance. So to dominate or to have IP, TCP/IP or IP in our industry or in our network is a growth in a traffic driven by access technologies that enables higher and higher bandwidth requirements. So you think we start with the age or 2G or 2.5G, then 3G, 5G, LTE, which promises gigs of traffic over the air from access to the core. To achieve this better networking performance, tight coupling has been required between the different plane, like the data plane, control plane, and the management plane, and between the hardware and the software. So we need to optimize on the optimization is very required to 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 achieve this, and also the openness to have interoperability within all those vendors. So if you see, all those components are basically contributed to the complexity of today's network, protocol, devices, and the network we use nowadays. So, so to get some idea about the SDN, to look at if you look at the history, Clean Slate project is one of the critical one which basically initiate this SDN buzz or SDN key things. So it was initiated by the researcher at Stanford University back in 2006 with two important questions. So, so it says that the first question is, with what we know today, the knowledge we have, if we were to start again with a clean slate, how would you design a global communication infrastructure? And number two is, how should the internet look in 15 years? So these two key components, and the mission of this project was to reinvent the internet, right, with the knowledge we have today. And it's significant that these works came out with the research community and not operators or vendors. So I would recommend you highly to have a look at this Clean Slate project and get some idea about the history or the motivation behind the SDN. So the outcome, so one of the outcome or of this Clean Slate project was internet infrastructure, OpenFlow, and software-defined networking. The output of this activity was the seminal paper known as OpenFlow, enabling innovation in campus networks. This work kicked off the SDN movement, and the networking world would never be the same again. So I have this screenshot. You just have a quick look and see This paper is mostly or the submitted or initiated by the academics, not by the operators or the vendors. So, so with the OpenFlow, the initial problem, the problem we're trying to solve with the OpenFlow is we need a mechanism for the researcher to run experimental network protocols, right? So the clearly network protocols need to run on a network devices such as routers and switches. To do so, we have two options, right? So the number one is to have an open software and hardware platform, which will enable a PC-based x86 PC, or even a specialized hardware such as NetFPGA uh, did not provide the required performance or scale or the port density required to do all those packet forwarding performance in a meaningful way. The number two, the second problem we have, or the option we have is the commercial solution. But the problem with this commercial solution is software was closely coupled with the hardware, so it's too close and inflexible, and it's too expensive. And we have dependency on the vendor, so we need to, for any new initiative or new implementation or new protocol design, we need to work with the vendor, and there is some implementation issues or time required to have that in place, right? So given the above constraint, how do we come up with a solution that would allow the user of a commercial grade routers and switches to influence packet switching and forwarding behavior in ways which we are not natively supported by the other platform? So that's one of the problem we try to solve with the OpenFlow. So the solution we have is uh, before going forward is really important to make a clear distinction between the control plane and a data plane. As we stated earlier, the router has two basic functions. So it determines the network paths or the routes. So, and if you remember for the first few slides, we explained that we need a routing protocol or algorithm to calculate the forwarding path, which is done by the control plane. And when the calculation is done, when we have the path ready, then we forward all those packets to the destination, right? So this one is basically then done by the data plane. So there's the difference between the control plane and data plane. So to address the question of how to run an experimental protocol on live network, the solution that the OpenFlow, the Clean Slate project come up with, researcher come up uh, with uh, with with the solution of completely remove the control plane functionality and move it to an external controller, right? So we will move all the intelligence to some of the external devices, and to abstract the forwarding plane on a switch as a flow table so that all switches appeared similar from a forwarding perspective. This was important because forwarding tables are very hardware dependent. Right. So the first one, what we did is we moved the control plane to external devices or some intelligence to some external devices, and we make sure that only the down forwarding is done by the switch as a flow. And use a standardized interface, OpenFlow on wire protocol or some other protocol over a secure channel that allows the controller to manipulate entries in the flow table of the switch. So it's interesting to note that router vendor had done these or doing these things for quite a long. So if you see all those modern routers like Cisco, Juniper, Huawei, Alcatel Lucent, you name it. So they basically have the separation of control plane and data plane physically by using control card or line card or so on. Right. So the initial concept of the OpenFlow was based on the Ethernet switches, right? So we see two types of OpenFlow switches has been defined. One is the dedicated OpenFlow switch that do not support normal L2 or L3 processing. These are essentially dumb data path elements that forward packet between the ports. And the second one is OpenFlow enabled switch. So those are commercial switches enhanced with OpenFlow capabilities. So the concept of data plane and control plane separation seemed like a good solution that did not require vendor to expose the internal working of their switches, but still allowed manipulation of the traffic path. The intent of this model was that the controller would have sufficient intelligence to determine the network path, which it would then push down to the new dumb network elements, which running some kind of open flow stack in it, right? Any questions so far? So these are the basics of SDN and how we move forward. So let's look at how the OpenFlow and how it works, right? So if you look at this uh, diagram here, I say that we move the control function to a separate entity or device, which known as OpenFlow controller, and we use the OpenFlow protocol, some kind of secured protocol, uh, to to push the flow to the switches, and we can see them as a flow table. So let's look at how this OpenFlow works uh, uh, in router and switches. So as I said, the OpenFlow controller is responsible for adding flow to the flow table and also deleting or modifying them. So there are a few approaches to do so. So the first one is the reactive one. So flow are added as packet for a new flows are detected. So it add all those flow in the reactive model. The proactive is flows are based on advanced knowledge. So controller basically push all those flow before any packet or packet forwarding starts. Or we could have a hybrid of reactive and proactive. So what it says that if you look at this flow table, it says that if we match a particular header in flow 1, then we'll forward it to port 1/1. If it match a particular flow with a tag of flow2, we could drop it. Or if nothing match, we can send the instruction to the controller, and the controller will make a decision whether we should drop it, forward it, or ignore it. So it's kind of a hybrid OpenFlow controller implementation. So in the flow, we have a header of field. So the in the header field, we have set packet headers field to match on. So we could match on specific header in the packet. Action is what we do when it matches. So we could forward it to an output port, or we send it to the controller, we drop it, we set additional header, and so on. And the counters is how many count or how many is basically for the statistics, how many packet match with that specific flow. So as I said, when a packet enters to the switch, if the header, it parts the header, and the header fields are looked up on the flow table. So if it does match, so it sets the associated action. If there is no entry, so it depends on the flow table whether it drops it or send it to the controller. Right? So we could have a single controller can manage a multiple OpenFlow switches. So if you look at here, we have one single controller which could maintain 1, 2, 3 or multiple n number of OpenFlow enabled switch. But ideally, we should have redundancy in the OpenFlow controller. So if any of the controller goes down, it will not impact the whole IP network, right? So it's not necessary that you need an individual controller for individual switch. So what we have as an OpenFlow today, because so in the early days of SDN, OpenFlow was almost synonyms to the SDN. So people think SDN and OpenFlow is the same thing, but as it continues to evolve, there are multiple revision of protocol, and the current OpenFlow version is version 1.5.1. So the today's OpenFlow is related to being just a part of greater SDN architecture with other protocols competing with it and also completing it. So it's however the spark, the lead of the fuse that start the fire, and that is the SDN. So some of the vendors might say uh, that their device are SDN capable, but they are not doing OpenFlow. Is absolutely okay. They could use some other mechanism to manage their devices on the fly. So it's not necessary that OpenFlow and SDN is the same idea or the same concept. So before moving forward, I'll look at the implication of OpenFlow. So for the explanation or for the discussion we had so far, from the perspective of OpenFlow, there are two primary implication of network architecture. So the first one is that the control plane is physically decoupled from the data plane, which basically forwards according to the decision passed down by the control plane, number one. Number two is the control plane is consolidated and centralized in a single software control plane, which controls multiple data planes. Previously, it was 1:1, right? So we have the control plane and data plane in the same switch. Now we decouple the control plane and centralize it. So it could be n×1 now. So you could have one single centralized controller which maintain multiple OpenFlow enabled switches. So the birth of now, if you look at the bigger matter of SDN, how it came about. So the separation of control plane and data plane was not an objective in itself, but was a consequence of a compromise approach taken by the OpenFlow, right? And this approach, however, create a new era of programmability that has been vastly enhanced with the new architecture and capabilities. And number three, the term SDN or software defined networking itself was coined in the article about the OpenFlow project and as Stanford. So I have the reference where in the Stanford they mention OpenFlow project and the SDN. So the emergence and evolution of SDN. So OpenFlow was the starting point, right? So it creates it enables an era of programmability, as I said, something that was not thought to be possible previously. But a complete decoupling of the control plane and data plane has proved to be impractical, right? So it might not be practical all the time. So we could have to solve all these problems. The industry had spent decades solving and refining or resiliency, scalability, convergence, redundancy, and it creates a new thought for us that if we have OpenFlow, how do we build network topology, right? how we react quickly on the network failure, how we address controller redundancy, and so on. So if you look at the SDN architecture today, practically what we have today is a hybrid approach where some elements of the control plane remain distributed with others are centralized. So many different architectural models were spawned from initial OpenFlow concept, and we will cover few of them in later slides. And all of them aspire to achieve the goal of agility of network programmability. So how we define an SDN? As I said, is one of the most hyped concept in the history of networking. And the original definition of SDN was on one that is still promoted in the Open Networking Foundation or ONF, and it defines it as the physical separation of the network control plane from the forwarding plane, and where a control plane controls several devices. So that's the definition in ONF. And this defines in how to narrow to describe an SDN nowadays. So in terms, SDN itself has been overloaded, almost I would say abused to many things, some of which leave no relation to what is originally stood for, right? So the vendor have been quick to attribute its term to any capability or any solution or any programmability that involves software, automation or programmability, they would rather define it as an SDN, right? So for our purpose, we define SDN as a new approach to networking that provides greater network agility and flexibility by automation is really important. So automation through enhanced programmability and open interface. So it should be an open interface so that I don't have any dependency on the vendor. Number two, disaggregation and abstraction. So I have abstraction layer, so I don't have to deal with the underlying layer. I can use some abstract language to influence the underlying layer. And centralization of network control with real-time network visibility. So these are the few things we need to achieve. And if I do a quick recap of the keywords which we are focusing on, the number one is the automation. Number two is programmability with an open interface. And we have an abstraction layer with a centralized network control, centralization of the control plane where we have a real-time network visibility. So these are the key components we try to achieve by having SDN. So the objective and the benefit of SDN. So I could say like 4 or 5 benefits, but to go one by one. The first one is the agility. So the biggest bottleneck to deploy new services nowadays is to creation and delivery, and we need to integrate with our OSS and PSS, right? And by using the concept of abstraction, SDN can allow quicker introduction to new services for faster time to revenue or time to market for the vendors. Automation is a service provisioning by end user services, what I say. So we could provision our network infrastructure, or we can automate our whole service chain. Or for example, we could have a self-service portal for our customer so that they could automate the whole process and provision new services for their new circuits. CapEx and OpEx optimization or reduction. So the simplification of network elements will cause reduction in hardware and network operation cost, and which have a better TCO over your CapEx and OpEx. Programmability is achievable via abstraction with the open and simplified interface. And to do so, last but not least, we have a centralized control where we could see end-to-end optimization. Optimal decision can only be made with a complete knowledge of the network, and we can see the end-to-end service and do the network management, and which is one of the major objectives for the SDN. So if you see in today's SDN standard bodies or SDOs. So there are a couple of key organizations. The first one is ONF or Open Network Foundation. They're more focused on promoting open source software as a de facto standard, and they make sure that there will be interoperability between all those solutions. They also accelerated the development of Open SDN to free end user from vendor lock-in paradigm, uh, and they're more focused on evolving the OpenFlow standard to deploy or develop new capabilities which will expand the SDN benefits. The next one is ITF, Internet Engineering Task Force, is development of IPMPLS protocol, and their efforts include forces, segment routing, BGP link state protocol, and so on in SDN. We have a Metro Ethernet Forum. So they define the life cycle of service orchestration and management capability in the SDN. We also have ITU, which does a specification with SDN framework, and the Broadband Forum is how we could have SDN in broadband access environment. So to look at the architecture, the first one we'll discuss the ITU framework, defining ITU TY.3300 specification. Is one of the simplified framework for SDN. Though it is quite simple, but it forms the basic for just about all of the other frameworks and open source implementation. So if you see here, we have the application layer, we have the controller. Application is basically the orchestration. Then we have the controller, and we have the network resources. Right. So the first layer, the application layer, is where the SDN application specify network services or business application by defining a service-aware behavior or do all the orchestration. So these applications interact with the SDN controller via application control interface or API. So in order for the SDN controller to automatically customize the behavior and the properties of the network resources, the programmability of SDN application make use of the abstract layer or abstract view of the network resource provided by the SDN controller. So then we have the middle tier is an SDN controller, which basically has all the intelligence within it, and it does the signaling to instruct the flow or push the flow to the network resources, and the resource layer is basically does all the flow, right? So this is the simplified way of or the simplified architecture of the SDN framework. The next one is basically by IETF, right? So it's more on a complex one, but you could have the details explanation in RFC 7426. But if you look at the same here, so we have the application plan, Then we have the control plane, and they divided in a control plane and a management plane, the controller, and we have the forwarding plane. So if you try to compare this one with the previous ITU SDN framework, overall is the same, but there are more details on how this framework will work, right? And the next one, we would rather say to have this combination from IETF and ITU and other frameworks, we come up with a architectural framework by ourselves. We could say the APNIC framework in more details information. So if you see in general or in major, it has all these three layers, but what are the protocols we are used? So we have the application at the top. We have the network service abstraction layer, and where we have all the controller, and we use what protocol to influence the data plane. So we also have two concepts of the keyword, which is very important. One is northbound interface, and one is southbound interface. So we will say this north and south with the perspective of controller. So anything within application layer and network layer is basically northbound interface. Anything with the application layer and the data plane is basically southbound interface. And we have the protocol which you use could use to communicate with the northbound or southbound interface. So if you see with the application, I will clearly. So if you see with the application and the node or the network service abstraction layer or the orchestration we could do with the API, it could be REST API or REST conf, conf, XMPP, and with the controller or with the southbound interface with the controller and the data plane, we use all those SDN enabled protocols like BGP-LS. We could use SNMP, OpenFlow, netconf, and so on, right? So in next few slides, we'll try to explain all those elements in more details. So the first one is the application plane. So it's basically the consumer of the network and maybe the end user application or network operation applications running on these application planes. So the application could be our voice system, our end customer, self-service portal, and so on. So the northbound interface is the mechanism for the application plane to consume services to the network. So the high-level protocol language, just like netconf, REST API, RESTconf, or XMPP could be used. And the network service abstraction layer, we have application plane, like which will normalize the network and service construction via Open API interface. So most of the cases, the popular one is the YAML model. And the key to ensure that the application plane is running and how services are actually delivered, all they have the visibility in the external element of the network. So this key to ensure the agility of the new service creation. So the next one is the control plane. The control plane here, or the southbound interface, is basically the controller or known as the brain of the operations. So it translates all those high level, like what we instruct by REST conf or REST API from northbound interface and convert them to instruct the resource layer. So and we collect all those key functions and use to manage in a distributed fashion to explore the topology discovery, traffic engineering, resource management, route selection, service configuration, and so on. So there might be a potential requirement to have a communication between the controller and we sometimes say as east-west bound interface. And the southbound interface is basically which you use to communicate with the data plane. So in the southbound interface, we have so many options and so many protocols, and which includes the OpenFlow, which we discussed earlier. We could have BGPLS, BGP Link State Protocol, which allow the topology discovery. Where we could have PCP for centralized path computation. We could IPIX, SNMP, NetConf, and so on. So all of these have a common purpose, and the purpose is to insulate the application plane from device-specific configuration information. And the device-specific details abstract from a higher layer to the controller. So we don't go in details with, or the higher layer don't have to deal with all those low-level configuration, the data plane. And the data plane, we have the traditional dumb data plane. It could be physical or virtual, and it could be router switches, white box, soft switches, and so on. And augmented by SDN-friendly protocols such as segment routing could be used in data plane only also. So if I try to summarize the key SDN use cases, so the first one is the data center automation. So is one of, or I would say mostly widely developed and deployed mature solutions. So far all the solutions mostly data center centric, and it could automate the network connectivity via overlay networks with a multi-tenancy, multi-vendor solution. SDN1 is catching up, so it's the extension of data center automation concept, able to integrate NFB with that one and site connectivity via overlay networking. Service automation and provisioning, so we could use direct customer access portal. We could give them a feature to have bandwidth on demand during DDoS attack or service provisioning if they require, and so on. And the last one is the network optimization. When we have a centralized view, we have better understanding on the network topology, and we can fine tune all those issues much better when we have some centralized controller at the top. So if you see the solution we have, or the project, open source project for the SDN, there are two. One is the Open Daylight, is the Open Daylight Open SDN platform. So it's kind of a de facto for the Open SDN platform. So the key use cases for Open Daylight is automated service delivery, cloud and NFB, service resource optimization, research, education, government, visibility, and control. So it supports OpenFlow, OpenFlow table platform or TTP extension, NetConf, BGP, PCP, and CAPWA, all those protocols supported. And it uses interface with OpenStack and Open vSwitch through OVSV SDP integration. The second one is ONS or Open Network Operating System, is founded by ON Lab and part of the Linux Foundation. So these are the two well-known or well-developed open source projects for SDN. So as I start with my session, as I mentioned, that there is some confusion and with our idea that OpenFlow and NFB might be the same thing, but it's not really true. There's some difference between SDN and NFB. And from the technical point of view, so the SDN is basically the physically decoupled network control plane with the data plane. And the NFB or network function virtualization is basically physically decouples the network software from closed proprietary hardware system. So if you see while SDN has its roots in the research community, NFB is strongly operated by the operators like SDN. The key objective of NFV was to improve network agility by reducing dependency on proprietary hardware. So if the network application could be run on a cost of commodity hardware, significant benefit could be achieved via a homogeneous hardware or x86 PC, which we could buy out of the box or from the market very easily. Right? So neither SDN and NFB are directly dependent on each other. So there's no dependency. You could have SDN, you could have NFB, or you could have both. So however, but the significant benefits can be realized by using both of them together. So in fact, many of the NFB use cases are enhanced with the adoption of SDN capability. Right? So that's what I have so far for today with the introduction to SDN. So if you have any question or if you need any further clarification on introduction to SDN, I'd like to answer those questions right now. Any question? If you have any question, you could type it in the chat box. Okay. So what I'll do next, I'll share the link where you could download these slides. Or if you have any question later, I'll share my email address with you. So feel free to drop an email if you have any query, if you have need further clarification. I'll have to answer those questions. So if you don't have any queries so far, I'll finish it for today. So thank you very much for attending today's e-learning. Hope to see you soon in future e-learning session. Thank you.